Hey, it's Mrs. Wheatby, and I'm back for Unit 2 video lesson number 8. We're going to investigate Bohr's model of the atom. But first, we might wonder, what are we going to do with all this information that we learned about the dual wave particle nature of light? Well, we're going to apply that to the newer discovery of the atom as we continue in our lessons on atomic structure. So what scientists were looking at is they were looking at these emission spectrums of different elements. And so what is an emission spectrum? Well, it is a set of frequencies of electromagnetic waves that are emitted by atoms of elements. And that still is kind of a little fuzzy. So let's take a look at what we mean by that. So an element's atomic emission spectrum can be obtained by passing the light emitted from that element through a prism. And once you pass that light through a prism, then that light is broken up into individual lines of color, each with a specific wavelength, frequency, and energy. So this is what scientists saw. So this is a gas tube, and when you add energy to that gas tube, then it glows with a certain color of light. And so if you pass that light, direct it through a set of slits so you have that light beam going in a straight line, and you pass it through a prism, then what that prism does is it breaks up that color into these individual color bands. And we see here, this would be the atomic emission spectrum for hydrogen. And so although we can't really see it in this gas tube, that it glows like a purplish pinkish color, a violet color. And we pass that through the prism, and when we do, that color breaks up into these 4 individual color bands that we see. So it's like that mixture of colors is what gives us the color that we see in the tube. But these are like fingerprints. They're like an element's DNA. So the atomic emission spectra are unique for each substance, like a fingerprint. And if we haven't, let's say, a gas tube, we don't know what's in it. When we pass the light it emits through a prism and we see an atomic emission spectrum, that is very specific for that substance that would be in that tube. That's actually how helium was discovered on the sun, through atomic emission spectra, and wasn't until it was actually discovered on Earth that helium was considered to be an element. Here are some other atomic emission spectra. Here's neon and magnesium, calcium, hydrogen, and sodium. And you can see for each one, very, very different color bands of electromagnetic waves. Niels Bohr, in 1913, he worked in the group with Rutherford. Remember, Rutherford did the gold foil experiment and discovered the nucleus. He introduced a quantum model for the hydrogen atom. Now, look at that term quantum. We've just talked about that. So, specific energy model for the hydrogen atom. He proposed that the hydrogen atom has only certain allowable energy states. One is the ground state, which is the lowest energy state of an atom, and then the other is the excited state, or the state of an atom after it gains energy. So if we kind of take a look at it in terms of, we have the nucleus with our positive charge, and let's say we have our empty space here with the electron. Okay, and this would be our ground state. And another thing Niels Bohr found is that electrons are located in orbits, these circular paths around the nucleus. And so let's say now we're adding some energy to the system. Let's say we heat it up. We heat up an element, and so now that element gains energy, but it's particularly the electron that is gaining the energy in the atom, and that electron is moving from that first orbit out here to this second orbit. And so that's said for that atom to be in its excited state. as we showed that it gains some energy. He also related the hydrogen atom's energy states to the electron within the atom. So the electron moves around the nucleus in certain allowed circular orbits, which is defined as fixed, definite circular paths where electrons can be pinpointed. So he's saying we can definitely know the location of an electron. It's right here in this particular orbit. Bohr was also able to calculate the radius for each of the orbits and found that the radius increases the further from the nucleus that the electron gets. Each orbit was assigned a number, which was given a symbol n, and that number is called a quantum number and refers to the energy level. So when we say that n is equal to 1, this refers to the first energy level. N is equal to 2, that refers to the second energy level, up to n equals 7, and that is the seventh energy level. So let's take a look at what we mean by the excitation of an atom, or an atom that becomes excited. Let's say that we're going to draw this right here, and this is going to be the nucleus. So we're basically cutting this element, or the atom, lengthwise. And this is the first energy level, so this would be ground state. So we're going to put our electron here, and it's going to be in ground state, the lowest energy state. And so here's what happens. That electron is going to gain energy in some way. It can be heated, it can gain electricity, but no matter what, when you add energy to the system, it's not the entire atom, but it's the electron in the atom that's going to move from ground state to a higher energy level, which is its excited state. Now, in the excited state, that electron is very unstable. And because it's unstable, what it is going to do, it's immediately going to drop back down to a lower energy state. Okay, so it drops down to a lower energy state. And whenever it does that, it has to release that excess energy. And it releases energy in the form of a photon. I hope you're writing this down because it's an essay question. Releases energy in the form of a photon. Well, we know that photon has energy, and if it has energy, it's going to have a specific frequency, and if it has a frequency, it's also going to have a wavelength. And that wavelength is what we find in that electromagnetic spectrum, in the visible light spectrum, and the color that we see. Okay, so excitation of an atom, and really the electron, that electron is going to gain energy. It's going to move to a higher energy state, the excited state, very unstable, so it's going to drop back down to a lower energy state, releasing that excess energy in the form of a photon. That photon has energy, frequency, wavelength, and that equates to the color that we see. So at ground state, let's say n equals 1, which is the first energy level. The electron is closest to the nucleus, so it has a very strong attraction to the positive nucleus. So it needs less energy to stay within its orbit. So those electrons in the first energy level are going to have the lowest energy. And as we move to energy levels further from the nucleus, then the amount of energy is going to increase. And let's take a look at why. So the attraction becomes weaker between the electron and the nucleus because you're increasing that distance. So therefore, the electron needs higher energy to stay within its orbit. So the further away from the nucleus, the more energy the electron is going to have. And the electron basically possesses the same amount of energy of the energy level. So here's what Bohr found. He found 3 different series of atomic emission spectra for the hydrogen atom. So these are the lines that we would see in the visible light spectrum, and there are actually 4 of them. We show 3 of them here, but there are actually 4. You have another purple one. And so this is when the electron gains energy and it falls back down to the second energy level. Those are the lines that we see in the visible light spectrum, and this is called the Bohr series. Those lines that are found, the atomic emission spectrum within the visible light spectrum of the atomic emission spectra. And then we have an area right here where the electron falls back down to the first energy level. This is called the Lyman series, and these lines would be found in the ultraviolet region of the electromagnetic spectrum, and we really can't see them with the naked eye. And then there's another series called the Paskin series, and this is where the electron falls down to the third energy level. And this would be in the infrared region of the electromagnetic spectrum. So it's only the lines we see when the electron falls down to the second energy level, and that again is called the Bohr series. So here's Bohr's model of the atom. You have the nucleus with the protons and the neutrons in the center, and then you have the orbits, and there are 7 of them, and those orbits are circular defined paths, so you would go out to 7 energy levels. And that would be Bohr's model of the atom. And this goes out to the crew. This is Mrs. Wheatley. So long for now.